in a broader sense, this is part of an area which should title the chemistry of protein because of the special characteristics of amino acids and because of the very large different structure involved. This tape will start with amino acid. We turn to amino acid to be that point of the amino acid chain is rather like a branch or a side chain, and this is referred to specifically as the side chain portion of the amino acid. Thus, a part of the amino acid is involved in the fundamental chain of a protein structure, and a portion of each amino acid sticks out from this chain as a side chain. This side chain is different for each of the 20 to 24 amino acids. These side chains have a variety of different physical and chemical properties associated with the physiological function in its normal uncellular environment. Some chains have acidic properties. Some are highly some will be properties in a protein deep slot will discuss at length how the physical and chemical properties of the particular side chains of the amino acids are heavily for the three-dimensional structure of protein, as well as allowing the protein to serve its normal physiological role. Now, with this rather brief introduction, let's turn specifically to that. And as you see on the slide, the description of how the hydrolytic breakdown of a particular protein molecule will result in this of amino acids. The protein is a large structure. It has a molecular weight which is usually rather hard to define within ranges, but according to some authors starts at a minimum millions. Actually, the bulk of proteins are probably in the 20,000 to 100,000 molecular weight range. In any event, regardless of size, the hydrolysis of a protein molecule can be accomplished in the laboratory in a number of different ways, and this is briefly indicated. First of all, hydrolysis can take place in an acid environment or in a basic environment, or by means of specific enzymes. These are proteolytic enzymes which have the ability to hybridize peptide bonds at approximately neutral pH in really very mild conditions. The mechanism of automatic hydrolysis of protein is that which is unit addition of dietary protein, also used in the breakdown of tissue proteins in the normal turnover of body constituents. The amino acids which arise from protein hydrolysis are 20 to 24 in number. The molecular weight of the amino acids is of 75 to some or 200. Now we'll turn to the slide. We'll briefly look at some of the general methods of classification of amino acids. These classification methods are obviously rather arbitrary, and they are based primarily on structure with little interest in physiological. And it does serve some purposes, at least to classify the amino acids in this way, and your textbook all follow a scheme either like this or slight modification of the scheme. First of all, there is a very large number of amino acids which falls to a class of neutral acids, and they're actually indicated on the center of the slide. The neutral amino acids have the same group as carboxyl groups, usually one of each. These can be assigned to serve major classes. Acids and so forth. Our second major class of amino acids is the acidic amino acids, having an excess of carboxyl groups, usually 2 carboxyl groups and 1 amino group. But the excess of carboxyl groups to amino groups gives this acidic characteristic to the structure. Specifically, the third class is that of the basic amino acids, and these are those which have an excess of basic groups. The basic groups are not necessarily always amino groups, but they are structures which behave with basic characteristics, and accordingly this major classification. So much for classification. Let's move on to a typical generalized structure of an amino acid. And on slide 2 we see in 2 different representations the general structure of an amino acid. Now there are many features that I think we can concentrate on here and apply some of these principles throughout the rest of the discussion. First of all, you will notice that one of the carbons is labeled the alpha carbon, and this is according to the nomenclature which characterizes carboxylic acids. With any carboxylic acid, the carbon next to the carboxyl group, the one immediately adjacent, is referred to as alpha carbon. The second is the beta carbon, and so on. But of course, beta carbon is shown on this particular slide. The amino acids which are found in proteins are alpha amino acids, and the basis for this term is represented on this slide. It's diagrammed on the slide, and it shows that the amino group is on the carbon which is alpha to the carboxyl group, on the alpha carbon. A second feature we put on in this slide is that the alpha amino acid here pictured in the L configuration is based on the nomenclature which is originally by in carbohydrate chemistry, and the assignment of the D or the L series according to the spatial arrangements of the four groups surrounding the symmetric alpha carbon. These groups, as indicated here, are all different, and if they are, the compound has optical characteristics. The important feature is that of the amino acids found in nature, essentially all of them are the L configuration. There are a few exceptions to this statement, but these are rather bizarre. For the purposes of our early discussion, it is sufficient accurate to say that amino acids found in nature are of the L configuration. The L configuration is that structure which is related in the relation of the phenyl groups to the carbohydrate L-glycerose. Another feature on this slide is indicated by the R portion, the generalized portion of the amino acid which is by R for any kind of a radical. The R represents the side chain portion of the amino acid which was alluded to earlier. In contrast, the amino group, carboxyl group, and the carbon between these two structures, the alpha carbon, are the chain-forming portion of the amino acid. Now, still another point that is demonstrated on this slide is that the general formula for an amino acid can be shown in two major and different ways. On the left is a non-charged species, and on the right is a dipolar or charged representation. The structures indicated are essentially identical for discussion purposes. Some of textbooks will show amino acids always in uncharged form, where others will use exclusively the ionized or dipolar form. Now, with a full understanding of the way in which the ionizable groups of amino acids behave, it is possible for discussion purposes to follow either of the conventions for representing amino acids. In order to expand this discussion a little bit, as amino acids are concerned, ionization of these structures, let's go to the next slide. Now, in the center of the slide, we added the ionized form of the general formula of an amino acid as was seen on the previous slide. Now we will see what happens to the ionizable groups when a solution of the amino acid becomes more acidic as to the left, or when a solution of the amino acid becomes more basic as to the right. Essentially, the center structure, the dipolar structure, is that which does exist in solution at near neutral pHs. And since most cellular pHs are near neutrality in living systems, this is the ionic species which is in greatest abundance. Now, if we consider this structure in the center, it has a zero net charge, as is indicated on the bottom of the slide. If we move into strong acid, as to the left, if we add acid to the structure in the center, we find the species as is shown on the left of the slide. You will notice that this has a net +1 charge. The ionization of the carboxyl group has been depressed in the process. The carboxyl group is now non-ionized in strong acid, and we'll go back to this in greater detail later on. Conversely, if we move back to the near neutrality situation, we have the structure as is seen in the center. And then if we move into a strong base, we will find that the structure as seen on the right occurs, namely the proton is lost from the amino group, and we have then a net negative charge on the amino acid. The structural species which is found in the center, the zero charge species, has another name, and that is as the Zwitter ion, and that is indicated here on the slide. The Zwitter ion is electrically neutral. It will not migrate in an electric field, and that's in contrast to the other forms which we see here. Now, if we were to expand the generalized formula of an amino acid to an acidic or basic amino acid, which has more ionizable groups, then the picture gets more complicated. And we will be coming back to look at this subject at a later portion of this slide. So really at this time, without a full discussion at this point of the ionization of an amino acid, let's proceed on and look at the particular structures and then come back and look at the ionization principles a little later. Now, the one thing I do want to mention on this slide is that although the carboxyl and the amino groups have ionization properties, in a protein molecule, these properties are not of importance, because the carboxyl group and the amino group indicated on this slide, which contribute to the peptide chain, the peptide forming portion of the amino acid, when these are in peptide linkage, there is no possibility of ionization. And on the next slide, we'll see the generalized formula of a protein molecule, of a protein chain. And what I have here is a circle around each of the amino acids contributing to this peptide chain. This is a very small portion of a peptide chain. It should be many hundreds of amino acids in length. And this is indicated by the dotted lines at the end. In between each of the amino acids, there is a substituted amide bond, which has a special terminology of a peptide bond. It's a substituted amide bond. A little later we'll talk about how we would name these peptides, and a little later about the formation of these bonds. But for purpose of this discussion now is simply to indicate that the carboxyl group, which we had seen on the previous slide, and the amino group on the previous slide, which are in the peptide chain forming portion of the amino acid, are tied up and are not capable of being ionized. Now, you can also notice on this slide that a series of side chains designated by R and R prime and R double prime and triple prime and so forth, these are not involved in the peptide bond, but instead they are sticking away from the molecule. And accordingly, this is the reason these R groups are designated as side chains, and it's all the reason that the sides are important chemical and physical properties of intact protein, including the properties of ionization. If one of the chain groups is an isobroup, then the pH of the particular cellular situation in the existing ionization of the particular group. They'll go back and discuss that. At this point, let's take a look at specific acids and that they become initially acquainted compounds. We'll probably take a bit of time with several to briefly comment about some of the important roles of the particular amino acids as we try in order to give you a little basis for an acquaintanceship with this large series of compounds, where you will have a chance to study each of them individually. Now, first of all, on the next slide, we will start with some of the neutral amino acids, and specifically some of the aliphatic neutral amino acids. We see, first of all, in the upper left-hand corner, glycine. characteristics. First of all, it's the simplest amino acid. Its side chain is a hydrogen. Now, since it's a hydrogen, the alpha carbon is not asymmetric. There are two hydrogens on the alpha carbon. This is the only amino acid that does not have an asymmetric carbon. You will notice that I've indicated for glycine, as well as for each of the other amino acids that we'll study, one of the shorthand abbreviations, which is used, GLY, a three-letter abbreviation for the compound, and this is especially helpful subsequent times when describing long, intact protein structures and the amino acid sequences therein, instead of using the entire name. So the shorthand names are quite obvious and will be quite easy to learn. Alanine is the next in the series. It has, as an R group, a methyl group. Now this is L-alanine, and remember, all of the amino acids are of the L configuration, and they will be presented this way in the formulas. Designations will probably not be used each time. L-alanine has an asymmetric carbon, as will all of the rest of the amino acids henceforth. The other two amino acids on this slide are serine and threonine, and they actually are a different subclass in and of themselves. They are hydroxy-containing amino acids. They have these on a short side chain. And with a functional group such as this, there is the possibility for any of the various reactions in which an alcoholic group can participate. Threonine is an interesting amino acid also in that it has two asymmetric carbons. Thus there are four possible isomers of this structure, but of the four possible isomers, only one exists in nature, one highly specific, unique structure, and again we see the example in nature of extreme specificity in stereochemistry. Now, I will go from this series on to another group of amino acids, and these are the branched chain amino acids. These are aliphatic and neutral amino acids, but they're also referred to as the branched chain amino acids. It's a little more complicated side chains on these compounds. These are valine, having 5 carbons, leucine and isoleucine having 6 carbons each. Notice that leucine and isoleucine are structural isomers one of another. The names were perhaps not, again, the best selection, and this is true of all of the trivial names which have been assigned to these particular amino acids. They don't tell anything about the structure. Isoleucine is also an amino acid having 2 asymmetric carbons. Now you will notice one common feature of these branched chain amino acids is that in each branch, the side chain for each amino acid, there is only carbon and hydrogen. These are hydrocarbon structures, fairly small, but with characteristics similar to those found in large hydrocarbons. Specifically, they are not attractive to water. They are not attractive to polar groups. These are hydrophobic in nature. And often it's found in an intact protein. Several of these hydrophobic type of amino acids may be found in close proximity one to another, and there is then a mutual attraction between the side chains because of their similar physical properties. Now the next slide shows 3 aromatic amino acids. These are phenylalanine, tyrosine, and tryptophan. The complexity has obviously increased. The size of the side chain assumes a greater importance in the three-dimensional structure of the protein. You can well imagine that it simply takes more room for side chains of this size than it does for the side chains of the amino acids we saw, for example, on the first slide, glycine and alanine and so forth. Phenylalanine and tyrosine are very closely related metabolically. One is the precursor of the other. They also are common precursors of a number of biologically important substances such as thyroxine and adrenaline and so forth. The next slide contains the sulfur-containing amino acids, and here the question comes as to whether
this should be 2 or 3 in number. The first 2 amino acids, as shown, are very close structurally. Cysteine, the amino acid on the top, is actually almost a dimer of the structure in the middle, which is cysteine. You will notice that cysteine, the structure in the middle, has a sulfhydryl group, and if 2 of these cysteine molecules are combined in an oxidized fashion, the disulfide structure of cysteine arises. This has a very great importance in protein structure in that often one of the cysteine residues, the one in the center, is in a portion of a long chain, and another cysteine residue is at a distant position in the chain. These are combined both biologically and by laboratory trickery, potentially, into disulfide linkages, and thus 2 distant portions of a polypeptide chain are strongly held in close proximity one with the other. The other sulfur-containing amino acid is methionine, which has an interesting structure in that a sulfur atom is located directly between 2 carbon atoms, a kind of a unique structure which is not frequently seen. The next slide shows the heterocyclic or the amino acids, and here they are still in the neutral amino acid class. These 2 amino acids are proline and hydroxyproline. Now it's evident on inspecting these structures that the nitrogen is not a primary amine, but rather it's a secondary amine. And accordingly, the designation of these structures as amino acids is a little more accurate. Proline, the compound on the left, is widely found as a component of protein structure, but in contrast, hydroxyproline is not widely distributed in nature. It is found predominantly in proteins of the collagen class. Another interesting feature about these structures is that when a polypeptide chain contains proline or hydroxyproline, the bending nature of the chain, which is typical of all of the other amino acids, is changed in that there are restrictions in bond angles imposed on the carboxyl and alpha carbon and the amino group because of the fact that the ring structure actually exists. The next slide takes us away from the neutral amino acids to the acidic or the dicarboxylic amino acids. And these are specifically glutamic acid and aspartic acid. Now they may also be named in some textbooks glutamate and aspartate, and this is in the area of the different presentations which are possible with the structures of the amino acids based on their ionization properties. As is seen, each of these has 2 carboxyl groups and a single amino group. Now, when a structure such as glutamic acid or aspartic acid is in peptide linkage, the carboxyl group farthest from the amino group is found free, and accordingly will generally be in an ionized form at approximate neutral pH, which exists in living cells. These will have a negative charge in that the carboxyl group or the amino group will be ionized. These will contribute to the charged environment and to the charge characteristics of the protein molecule itself. Now there are 2 other amino acids which are very closely related to these structures in that these distant carboxyl groups, which are usually not involved in peptide linkage, in the next 2 amino acids are tied up as amides, primary amides. And the next slide will show these structures. These are specifically glutamine and asparagine. Now you will see that the nomenclature between glutamic acid and glutamate as a possibility for the previous structure, and now glutamine for this structure, will cause a degree of confusion, but we will discuss these throughout biochemistry so many times that this will be relatively logical as time goes on. You will see that the distant carboxyl function in each of these compounds has been replaced by an amide, and accordingly the ionic characteristics, potential characteristics of this structure are lost. It would really be proper to classify these structures in the neutral amino acids because They each contain a single acidic group and a single basic group. These structures, asparagine and glutamine, are incorporated into protein molecules, and as such, the amide on the side chain is electrically neutral. It does not contribute to the ionic environment, as would the carboxyl group of the similar compounds, glutamic acid or aspartic acid. The next slide in the series shows the basic amino acids, and we have listed 4 of them here. These are, again, a bit more complicated: histidine, arginine, lysine, and hydroxylysine. The first 3 of these are relatively abundant in nature, whereas hydroxylysine has a quite limited existence in a relatively few different protein structures. And yet, for the completion of discussion, I've included it here in this series. All of these structures have more than one basic group. In the case of lysine and hydroxylysine, this means 2 amino groups. In the case of an arginine, it is an amino group and a guanidine group. And in the case of histidine, it is an amino group and the imidazole structure, the ring structure. Now, at this point, we have completed the structures of the amino acids, and I think it would be wise to briefly review the material to date by means of a short quiz on the next page in your handout, number 11, page 11. You have a brief quiz covering the material we've talked about to date, and I would hope you would now turn off the recorder, take the quiz, and when you have completed the quiz, turn the recorder back on and move to the next slide, which will have the answers for the questions. Having completed the quiz, I will assume that the material presented therein is relatively familiar. Hopefully the question 7, which asked you to draw the structure of alanine and show what would happen to this in strong and weak base, if you were relatively successful on that question, you are pretty well prepared for the next material we'll talk about. Now, specifically, the next section will refer back to the ionization of amino acids, and on the next slide I have redrawn glycine in its various ionic forms, and we'll talk about this a little bit. Now, here we have glycine. The dipolar form is listed in the center of the page, the upper portion. The positively charged species, that which is found in acid, is shown on the left, and the negatively charged species, as is found in strong base, is shown on the right. In looking a little more specifically, we can see that the ionic species, shown on the left, the positively charged structure, can dissociate and can lose a proton, thus serving as an acid. It's a relatively weak acid, and yet the dissociation of this weak acid can be described and quantitated in exactly the same way as can that of any other weak acid. Specifically, the dissociation constant of this weak acid can be determined, as is shown on the bottom of the slide. And the pK for the dissociation, as seen, is 2.34. In similar fashion, the zwitterion, the species found in the center of the slide, can also serve as an acid and donate a proton. It is a much weaker acid than the structure on the left, but nevertheless, this can be experimentally evaluated. The dissociation constant for this second acid can be referred to as pK2, and accordingly, the pK2 has an approximate value of 9.60. Now, if these expressions are not familiar to you, it would be advisable to review material concerning pH and buffers and pKs and so forth. Now, with this description of some of the physical characteristics of glycine and its 2 dissociation constants related to various ionic forms, we can see on the next slide the determination of still a different value, that of Pi. Pi is the pH at which glycine exhibits no net charge. Glycine is at its isoelectric pH. This value can be calculated. It's the average of the 2 pK values for the dissociations of the 2 weak acids, which can be found as various ionic species of glycine. Accordingly, the Pi for glycine is 5.97. And this is relatively close to the Pi value for other of the aliphatic neutral amino acids. You will find in most of the textbooks tabular information as to the various pKs for the different amino acids, and from an inspection of a table of this nature, it's obvious that carboxyl groups dissociate with similar characteristics. The pK values or the K values are within a relatively close range one to another, and so forth. The information about glycine and its various pKs can be used to draw an approximate titration curve for glycine, and that we have on the next slide. The titration curve for glycine has 3 inflection points, and these are indicated by the small arrows. The first being at a pH equal to pK1, that of 2.34, at which point the ionic species would be 50% in the +1 form and 50% in the Zwitterion form. Another inflection point occurs at pH 9.60, pK2 value, and a third inflection point at the Zwitterion position where the pI of 5.97 is indicated. You will remember and observe that, as with the titration of weak acids, and here we have 2 weak acids being titrated, as each one of them is titrated, a point of maximum buffering occurs. And this is a point where there is an equimolar ratio between the conjugate acid and the conjugate base of the buffer pair. These are the pK1 2.34 and pK2 9.60 positions. In this titration curve, this is only a graphic representation of the kind of information as is presented with just the tabular information of the pKs involved with glycine. This does not actually tell any more than the pK values, and yet in a graphic form, perhaps it becomes more meaningful. Now, if the situation gets more complex, and we can see this on the next slide, considering glutamic acid. Specifically, glutamic acid has 2 carboxyl groups and 1 amino group, and the carboxyl groups have pKs of 2.19 and 4.25 respectively. The basic group has a pK value of 9.67. The ionic species are shown here, and if we were to look at these as conjugate acid, conjugate base pairs, we would find that we could set up 3 different dissociations and observe these as the 3 different weak acids are being considered individually. If we look at a titration curve of glutamic acid, we have this on the next slide. It's simply a little more complicated than that for glycine, as seen earlier. This has 3 phases in contrast to the 2 phases as titration of glycine. The first 2 titratable groups, the loss of protons from the 2 carboxyl groups occur relatively close to each other in the pH range. And the graph has been actually accentuated in these 2 presentations. The curve really doesn't break as sharply between pK1 and pK2 as has been put forth by the artist, but at least this gives an idea as to how the titration curve of acidic amino acid would look. Now, it probably would be wise for you to think about the basic amino acids, and with values which can secure from either a textbook or other sources the pK values of the various dissociable groups in the basic amino acids, you might draw a titration curve of one of these structures in a similar fashion. Lysine would be a good example, arginine, and so forth. Now, in addition to the basic groups that I have talked about, we have on the next slide some additional complications which can be taken into consideration when dealing with the titration curves of amino acid. Here I've listed 4 amino acids having other titratable groups other than carboxyl or amino groups. And in addition, I've listed for these groups the pK values. First of all, for the imidazolium group of histidine, for the guanidinium group of arginine, for the phenolic hydroxyl group of tyrosine and for the sulfhydryl group of cysteine. It should be possible for you with these values also, as well as those of carboxyl and amino groups, to construct titration curves for any amino acid, and thus have an appreciation, first of all, of the behavior of the dissociatable groups, and second, of the buffer capabilities of these various compounds at pH ranges. In these last several slides, we have examined some of the reactions of amino acids, those relating specifically to changes in the acidic and the basic groups which occur when pH changes occur. It would be possible to examine many other reactions of amino acids, and most textbooks have large sections in this general nature. Reactions of carboxyl groups and then reactions of amino groups, but these are not of any physiological significance. They are very helpful in the determination and the estimation and sometimes in the separation of amino acids, but I believe it is beyond the scope of this present discussion to deal with at this point. I would like to briefly go back to the polypeptide chain, look at the way the polypeptide chain is named. So next slide, I have diagrammed a short sequence of amino acids and have indicated, first of all, the shorthand designation using the three-letter abbreviation for each amino acid, and then in addition, the formal name which to this polypeptide. In naming this, I have used a convention which is universally used in peptides. Specifically, the name starts from the end of the chain where the amino acid has the free amino group. Thus you can see in this chain that alanine at the left, which has the free amino group, is named first. The formal name for this peptide uses the suffix YL, and thus alanyl glycyl glutamyl serine is the name of the peptide. The carboxyl-containing amino acid, the free carboxyl group, serine, is always last, and it does not have the suffix Y added to this in the formal nomenclature. We'll see here the advantage also in using the three-letter abbreviations ALA, LYS, GLU, and so forth. Now, in the final slides, I want to show you a bit about ways in which mixtures of amino acids are separated. In thinking about the total structures of proteins, first of all, structures evaluated would have to be broken down to complete amino acids. And this would leave a mixture, at least 20 or different components. These must be subsequently separated and then divided and quantitated. And this is not an easy job, because in the classes of amino acids, chemical and physical properties of many of the group amino acids are similar. Thus, much effort has devoted in determining methods adequate for reasonably separating compounds. Current most popular and most successful methods are chromatographic. On the side of a picture, another fanciful rendition of a two-dimensional pigmatogram, in which a mixture of amino acids was applied onto a piece of paper designated for chromatographic use in the left-hand corner, and the paper was subsequently developed chromatographically, first in one direction and in another, using solvent systems. The paper was dried and sprayed with a reagent capable of showing where an amino acid is located at the end of chromatographic procedure. Now, most of these sprays give single colors for all of the amino acids rather than a rainbow colors as are seen here.